it's visible. Yeah.
My name is Vidhya Lakshmi, and today I'll be presenting my AI capstone project titled A Decision Aware Multi-Modal Financial Intelligence Framework with Directional Edge Forecasting, Predictive Throttling, and Regime Adaptive Execution Control. Before discussing the framework, I will first present the problem statement and motivation for this research. The central problem addressed in this project is how to make reliable trading decision when forecast quality is uncertain. So the traditional financial AI system typically focus on generating predictions such as whether a stock price will move up or down. However, a prediction alone does not indicate whether the prediction should be acted upon. Markets are dynamic, noisy, and influenced by many external factors, making forecast reliability highly variable over time. The motivation for this work comes from several limitations observed in traditional forecasting systems. Many existing approaches focus primarily on prediction accuracy and often assumes that every prediction should be executed. However, in real-world markets, execution decision involves uncertainty, risk, changing market conditions, and varying forecast reliability. Financial decision making therefore requires more than accurate prediction. So this motivated the development of the framework that combines forecasting with decision control, predictive throttling, and adaptive execution governance, rather than relying solely on prediction performance. Recent advances in artificial intelligence have significantly improved financial forecasting through deep learning architectures and multimodal data integration. Despite these advances, most financial AI systems remain prediction centric. They focus on forecasting future price movements, but provide limited support for evaluating forecast quality, controlling execution decisions, or adapting behavior. So this project builds upon prior research in financial forecasting and transformed based modeling. Lim and other authors introduced the TFT, which is Temporal Fusion Transformer for interpretable multi-horizon forecasting, while Zohu and other authors proposed Informer for efficient long sequence prediction. Wasser, Batcher, and Spindler highlighted the limitation of prediction only financial AI system. Unlike prior work, my framework integrates forecasting with a decision layer, execution control, and realized outcome evaluation. Let's move on to approach. I developed an end-to-end financial intelligence framework consisting of 6 stages from data collection to adaptive learning. The system combines market, sentiment, macroeconomic, and graph-based information to generate forecast and trading signals. Execution decisions are regulated through utility-based evaluation and risk controls. Realized outcomes are continuously monitored to support adaptive learning and system improvements. The design follows a layered architecture, beginning with the multimodal feature integration. Market conditions are evaluated through regime detection, volatility, and stress indicators before forecasts are generated. Signal reliability is then assessed using confidence estimation and adaptive scaling. Finally, an ML-based decision layer applies filtering, position sizing, and risk constraints before execution and monitoring. Let's see how it is implemented. So the implementation uses a TFT to generate multi-horizon forecast across several prediction horizons. Model robustness is improved through multi-site training, hyperparameter optimization, and experiment tracking. Forecasts are evaluated for reliability, directional consistency, and realized performance. There is another layer called the MLV2 decision layer. This layer determines whether the signal should be executed, scaled, or suppressed within the live paper trading pipeline. This is about data collection. This project uses a multimodal data set collected from March 2018 through June 2026 across 10 major US equities. The data combines market price, macroeconomic indicators, financial news sentiments, cross asset signals, and graph based relationships. FinBERT was used to extract sentiment information from financial news. This diverse feature set was designed to improve market awareness beyond traditional price based forecasting. To simulate realistic deployment condition, I used strict walk-forward validation and sequential paper trading evaluation. Performance was assessed using directional accuracy, Sharpe ratio, execution volatility, and realized trading outcomes. The evaluation demonstrated stable directional forecasting performance across multiple equities and forecast horizons. Predictive throttling improved execution stability by increasing the ratio by approximately 19% and reducing volatility by over 60%. Sequential paper trading evaluation also revealed a measurable gap between predicted trade utility and realized outcomes. So, this finding highlights the importance of deployment monitoring and decision aware execution control in financial AI systems. So thus, I conclude by saying this project developed a decision-aware financial intelligence framework that combines TFT forecasting, FinBERT sentiment analysis, and predictive throttling. Experimental results showed meaningful improvements in risk-adjusted performance, with the Sharpe ratio increasing from 0.2 to 0.26, and execution volatility decreased by 60.4%. The sequential evaluation further demonstrated that the prediction quality alone is insufficient for reliable deployment. So, the key takeaway is that the decision control mechanism can improve robustness by regulating execution under uncertainty. Several opportunities exist to extend this research. First, the framework can be transitioned from paper trading to live production environment. Second, reinforcement learning may be incorporated to support more adaptive execution and throttling decision. Finally, expanding the relational graph and incorporating additional alternative data sources may further improve contextual awareness. Can I play the demo?
Sure.
There are two parts. First, I will play the part.
I'm sorry to interrupt.
Yeah,
Just a reminder, 5 minutes more.
yeah, sure. I think it takes just 2 minutes. Yeah, that's it. Yeah, thank you for your time and attention. I would be happy to answer any questions.
Thank you for the presentation. Professor Brian, would you like to ask some questions?
Okay, thank you. Mm, Lakshmi. So is there a particular reason thank you very much for sharing your your presentation. Is there a particular reason you chose this time period? You are restricting to um 2018 to 2026. Yeah, just trying to find out um yeah, the reason for choosing this time period.
Professor Brown, so the reason why I chose the time period, the particular time period is, so I'm using a API called Alpha Vantage. The Alpha Vantage API gives the historical stock price data only from 2018. So I'm following 2018 till the recent June 2026 by a live evaluation. So I'm getting the historical data from Alpha Vantage, which starts from 2018. Then it ends by 3 years, and then I'm starting my live prediction environment to collect more data for the recent years.
Mm. Okay, so it seems like the time periods include the COVID period, right? COVID
Yeah.
period where there is a kind of economic impact. So
Yes.
I think it is a good choice to have some sort of